said it was life, imagining the universe. And it's why I like coming to events that he organizes, because they knock me out of my comfort zone and make me think about something that I should be thinking about, but I haven't, which is, so I said back to him, well, what I'll talk about is imagining life in the universe, because that, in a sense, is what I'm trying to do, searching for life on other worlds. So, in my usual disorganized way, I forgot when I was giving the talk, but I knew it was today. So I put down today. And I'm just down the road here at NASA Ames Research Center. So, as Piero said, I'm in planetary science, but in particular, my interest is searching for a second genesis of life on other worlds. This is it's an interesting sort of job description. This time of year, you're filling out your taxes. There's a little box, occupation. I write, searching other worlds for alien life. The IRS has never audited me. They probably don't even want to know me. But that's really what I want to do. That's what I take as my job description, searching other worlds for alien life. So what I'll do is just briefly say why. Why is that interesting? And then I'm going to go to the imagining life on other worlds. How have we humans imagined life on other worlds, a second genesis of life, and then what are we actually doing right now? So why are we interested in the second genesis? Well, first, it would be comparative biochemistry, life 2.0. We'd have another example of life. On Earth, we have one example, shown very nicely by this diagram, the so-called tree of life. If you haven't seen it, I recommend it. It's one of the powerful unifying icons of science of the last 30 years. Just go on Google and type tree of life. The viruses aren't on it. We still debate over where to put them, but they're part of the same system. It's all one common biochemical, genetic, and evolutionary history. You can think of this as like a biblical begat table. This begat that, begat that, begat that, and so on. And that's life. And what we're searching for, the second genesis, is aliens. We have an operational definition, biochemical definition, not on this tree of life. They're not on our biochemical, genetic, phylogenetic tree. It doesn't say anything about where they're from, as I'll mention. For a long time, we thought aliens meant they were from another planet. So when I was a kid, if you were from Mars, you were an alien, and if you were an alien, you were from Mars. So alien was defined geographically. But that makes no sense. It makes much more sense to define them biochemically. If you're not part of our biochemical system of life, then you're an alien. Geography doesn't matter. Now, there's still some backward federal agencies that define aliens in terms of geographic locations, like the INS. But at NASA, we are beyond that, and we define aliens in terms of biochemistry. And what we're searching for, in some sense, then, is another type of biochemistry. We learn a lot by doing comparative biochemistry, but it also tells us that life is common in the universe. If right here in our solar system we found two examples of biochemistry, independent of each other, that would tell us very strong evidence that life is common in the universe. And I added an editorial comment, yay, that would be good to know. So how are we trying to get another example of life, the second genesis? Well, there's three human activities directed toward the second genesis. One is SETI, just down the road. Listen for them to call, right? Another is we're going to make it in the laboratory. And I'll come back to that really briefly. And the third is find it on another world. Now, I don't like phones, and you can see since I used a hammer for my laboratory icon that I'm probably not good in the lab. And so what I'm going to talk about is this one. As Piero said, I'm involved in missions to other worlds to search for evidence of life. So I want to turn now to sort of the perceptions of what a second genesis might be. And I want to start with this clip. Sounds now. Oops. Okay, thank you. Let me start this again. If I can figure out how to do it. Probably. No. Did we have... It was working there.
You can mute on your computer?
I can
Here's
do it,
something.
but very low. Yes.
Great,
Mic
thanks.
works.
Okay.
I run a complete spherical check on all life forms, radius 100 times. I've located on that, all of them. And I've located one creature moving rapidly through native rock bearing 201. And that was all. One creature in 100 miles. Exactly.
So there's several things I like about this scene. One is what convinced me that I wanted Spock's job, not Kirk's job. Second, it convinced me that I really wanted a tricorder, device that could detect life through solid rock. Now, if you remember this scene, it occurs about 12 minutes into episode 26 of the original series. Of course, you all remember that. The life form, the creature that they're detecting, is the poster child for a second genesis of life, silicon-based life. So if you go up to anybody and say, imagine a second genesis of life, a different type of life, they're going to say, oh yeah, silicon-based life. Of course, the logic for that is that silicon is right below carbon in the periodic table. This is the creature from that Star Trek episode, the Horta, and it looked just like something you'd recognize as life. It sort of scurried along and was floppy and slobby. And the only thing that sort of separated it from things we know is that its eggs were crystalline silicon. Right? So it was, and if you look at the literature discussing silicon life, it follows this approach. It says, well, we know how life works with carbon. It's kind of sloppy and gooey and flexible. Let's try to make silicon do that same thing. Let's try to figure out how silicon can make polymers and structural molecules that are like amino acids and so on. And I think that's just completely mistaken approach to silicon life. That's like you have a dog and the dog dies, and so you try to get another furry creature, turns out to be a cat. You try to get it to do all the things your dog did. Well, it's just not going to work. I tried it. But if you take the cat on its own and say, what are the sort of things that a cat can do, it can be quite enjoyable. If we take that approach to silicon and say, instead of trying to force it to look like carbon and have flexible molecules in a liquid environment, say, okay, well, it's going to look like this. It's going to look like a rock. It's going to be crystalline. It's going to be a rock. How do rocks get energy? How do rocks store information? How do rocks reproduce? How do rocks move? And you can come up with a whole interesting universe of how these creatures might live that's completely different. So there's no good science fiction story about silicon life that treats it that way. But I can imagine one, and if I did, I'd like there to be this dialogue in it. So one silicon life form calls back to the other and said, well, I've checked out these organisms. They're made out of carbon. And it's bad news and good news. The bad news is they move by flexing their bodies and distorting their bodies. Isn't that awful? Yeah, that's gross. They also leave little piles of biological material after them in various places. Oh, that's really disgusting. And the worst part is that they live and get energy by eating each other. Oh, that's just totally horrible. How could it? You said there was good news. What could the possible good news be? Well, the smartest of these creatures has figured it out. They get it. And they're building silicon-based life and systematically destroying all the other carbon-based life on the planet. So, okay, so it's not all bad news. I don't know if anybody will write that science fiction story, but if you do, please include that dialogue. The point is we have to reimagine. When we reimagine silicon life, we have to go really deep away from our prejudices to what makes life life. And no one's been able to do that. A little easier in the standard approach to imagining life not like us is to just replace the water with ammonia. That's real easy, real common, even done in cartoons. This was in the New Yorker in '62, alien lands, ammonia, ammonia. And this is, a lot of science fiction works on this idea where you just change what we know about life in little ways. And the two sort of defining novels in this genre are both by Hal Clement, a wonderful writer, basically Ice World, where aliens are coming from a planet that's 500 degrees centigrade, where they breathe sulfur gas and have liquid copper chloride. The only indication in the book that they are carbon-based is that they like tobacco. So that's a sign that they're carbon-based. And his other book, Mission of Gravity, is the other extreme. It's very cold, but now the liquid of the carbon-based life is methane ammonia. This is sort of a stretch of our organic chemistry as we would know it. And by the way, I went to the bookstore a couple days ago and found Ice World for $2. So I put it on the back table and the book crossing up there. So hopefully somebody who hasn't read it will take it and read it. More imaginative and more bizarre are Fred Hoyle's book, Black Cloud, and Robert Forward's book, Dragon's Egg. Black Cloud, Fred Hoyle was an astrophysicist, a very good one, got the Nobel Prize for his discoveries, just died 10 years ago. He imagined a cloud, an interstellar cloud, where the electromagnetic fields within the cloud were creating a life form. And it was, of course, intelligent. And all these books, fiction books, of course, the intelligent life that we're imagining has to be intelligent as a plot element. It's just not very interesting to interact with an unintelligent life form. There's no, the book won't sell. So there's intelligence. The black cloud is intelligent and benign. And it takes Earthlings and the cloud a while to realize that each other are intelligent. But here, it's the essence of life, it's electromagnetic interactions, period. Whereas Ford, imagining life on a neutron star, goes away. The only good, credible scenario for life that's not electromagnetic, he imagines life essentially based on the strong force, on a neutron star. And so it's not, life is not an assemblage of electrons, it's an assemblage of neutrons and gluons and quarks. And when his book came out, I was in graduate school taking a course on quantum mechanics, and the professor, Joe Dryline, pointed out that there's a scientific basis for thinking about that. That if you write down the Lagrangian, which is a mathematical function that tells you how the system behaves, for electrodynamics, bang, 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 blah, 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 you don't need to pay much attention to it, but notice that if you write down the same thing for quantum chromodynamics, the strong force, blah, 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 it looks like the same. There's a mapping. The terms here have terms here, terms here, terms here. The difference is that electricity has only 2 types, plus or minus, whereas the strong force has 6 types, 3 colors and their anti-colors. So if anything, it's more complicated. But his point, Joe's point, was that if life is a solution of this equation, life ought to be a solution of this equation too, because the equations look the same. It's a very interesting idea, taking the concept of life all the way up to linking it with the notion of the abstract mathematical equation that represents how that system works, the Lagrangian from which the equations of motion derive, et cetera, et cetera. And then pointing out that the same should occur at this scale. And since the charge, the coupling charges G versus E are so much stronger, everything will go much faster here, and that's a part of the plot element of the book. So that's how we've imagined it, some of the key elements in our imagination. But what are we actually doing? It's much more mundane, unfortunately, is we're going to the nearby planets and seeing what we find. What we're looking for is planets with water, because that's what we know. On Earth we have water, we know that it's good for life, so we're looking at planets for water. And amazingly, we have 3 good candidates. Mars had water, Europa has an ocean, and Enceladus has an ocean, and it's even got a plume coming out from that ocean. So we have 3 water worlds that we can look at. And as we get further from the Earth, we increase our chance of finding life that's really not related to us, that is what we're looking for, a second genesis. And Titan is in a special category because it's not a water world, but it's a liquid world. It's a world that has liquid, and the liquid is not water. So what are we hoping to find on these worlds? What are we searching for? Well, the approach is we're in a water world. The chemistry is almost certainly organic, carbon-based chemistry in water. So in that sense, it's going to be like us. But how much like us? Well, this is us. These are the biochemicals that we use to build life. The amino acids, the purines, pyrimidines, sugars. This page are the basic building blocks. I call them the Lego blocks, which stack together in combinatorially beautiful ways create life. Okay, you make all the amino proteins from these amino acids, stacking them up. And even though there's only 20 of them, if you stack them in different ways, you can make more different proteins than there are atoms in the universe. The combinatorial complexity is just that vast. And similarly with the other components. Life is also not just structure, it's information. And life on Earth all has the same common information. And this is shown really nicely in this comparison of the genetic, of a stitch of the genome of a variety of organisms, starting from my little brother, Homo sapiens, all the way down to E. coli. And you find the same words in all the genome. This is almost like saying, I am from Earth. All life on Earth shares these common segments in the conserved parts of their genetic material. So we have not just common structures, we have common software. So there's only one operating system on Earth. It's sort of like in the future on here, where instead of Macs and PCs, we'll only have Macs. Right? This has happened on life somehow. We're all down to just one operating system. So what might we search for in another water world where life started separately? Well, it might, for reasons that I won't go into, we would expect life to only use certain molecules. It doesn't use all of the organic chemistry, it just uses the key set of bricks over and over again, but maybe it uses different bricks. So that's the idea. Life, carbon-based, but we would recognize it as different because it would use different bricks than the bricks we use here. So here's a diagram to help understand that. Imagine you want to build a house. So this is what I call the ecological level. This would be equivalent to things like using sunlight to make energy, taking up CO2, swimming through the pond. This is life behaving ecologically. It's a house. And it's built out of carbon and water, ultimately. Both houses are built out of carbon and water. This house is built out of C atoms, and this house is built out of C atoms. But they differ in the way those C atoms are put together at the intermediate level. Here, the C atoms are put together in plastic, molded into blocks called Legos, and then you build a house out of Lego bricks. Here, the C atoms are put together in wood, carved into Lincoln logs, and make a house out of Lincoln logs. Both cases are houses. Now, many of you probably never heard of Lincoln logs. But when I was a kid, plastic, we didn't have Legos. They hadn't been invented yet. In fact, plastic hadn't been invented yet. So we played with Lincoln logs. But anything you can make out of Legos, you can make out of Lincoln logs. That, in a sense, this is a metaphor for what we're searching for on Mars, Europa, and Enceladus. It's still carbon and water. It's still going to ecologically look like life on Earth. Where it's going to be different is in the middle. How those carbon molecules are put together to form the structures we see. So what particular structures are the analogs of the Lego blocks? I'm going to focus on amino acids, because they're the ones where there's the most possibility of choice. So if you think of all possible amino acids, there's like 100 practically possible amino acids. Not theoretically possible, but practically possible. Earth only uses 20 of them. That's kind of interesting. We don't use all 100. We only use 20, more or less. And there's a couple exceptions, but basically we use 20. So we use 20 out of 100 amino acids. Of those 20, 10 we sort of inherited from Mother Nature. We think that those were made prebiotically, we got them for free, might as well use them. But 10 we had to invent ourselves, we being life. Right? And there's been a lot of work recently focusing on, well, why do we use these 20? Is there something magic about that set? And the answer is no. A study by Philip and Friedland a few years ago showed that there are other sets of 20 that can do everything that our set does. So we just picked a set of 20, and there's nothing magic about it. Other sets could work. You can imagine strange biology that might use the same 10 that they get for free, but a different other set of 10, or even stranger biology that doesn't have any overlap in our amino acid. This is still amino acid-based life. It's just different from ours. We could still probably eat it. Our digestive enzymes could break the peptide bonds, and we could oxidize these amino acids. It's very similar to us, but distinctly different. It would represent a second genesis, and we would learn a lot by comparing to them. One other thing about amino acids is they come in chirality, right and left. And so you could have not just this story, but its mirror image. And we think that would work too. We're not sure it would work, and that's why I put the rabbit in here. We're not 100% sure that the mirror world is the same as the regular world, but we think it is. Finally, Titan, which is a different story altogether, because there it's not water. There we don't know what the building blocks are. We don't know what to look for, but it's the only other world in our solar system with a beach, where liquid hits shore. The beach is liquid methane. There's possible reaction sources. I won't go into detail, but we don't even know how to search for life on Titan because it is so different from us. Life living in 94 Kelvin liquid methane has got to be different than life living in water. The only strategy that we could think of is search for its pollution. One thing that life is very good at is polluting. Polluting its environment. The oxygen in our atmosphere is a pollution created by cyanobacteria billions of years ago. Humans in their wisdom are getting rid of that pollution, restoring the CO2. Well, on Titan, what would be pollution by life would be the depletion of hydrogen. So that's what we would search for if we went to Titan. We wouldn't know how to search for their equivalent of amino acids. We can't even guess at it. And finally, I want to just say, second Genesis, we could make it in the lab. We could make a mirror image of life. Just take an E. coli cell and flip the chirality of all of its proteins, all of its DNA, all of its sugars, so it's exactly its mirror image. It should still be alive. That would be a second Genesis as well. Finally, if we do find a second Genesis, so what? This is actually a student asked me this, giving a talk at Death Valley. He said, well, what are you going to do if you find a second Genesis of life on Mars? And this is a good question because we don't know. We are unprepared for success. We're like the dog chasing a car. What are you going to do when you catch the car? You don't really know. What does it mean to find on Mars another example of life? I'm not going to answer the question, but I'll just point out that we don't know what the moral status of alien microbes would be. Suddenly we'd have another type of life, fundamentally different. And its sole representatives might well be microscopic. Microbes, we normally kill them. We kill them when we wash our hands, we kill them when we brush our teeth, and I encourage you to continue doing all those things. But we just kill them, whereas what if they were the only representatives of an alternate life form? Right? They would obviously command higher status. And you say, well, this is just sort of philosophical hand-waving, but in fact, I argue that it has implications for the way we explore now. And I've argued that we need to explore in a way that's reversible, just in case we do find a second Genesis and decide to take its interest into account. And then this is the end, my clue that it's the end of the talk, and maybe we have time for questions.